Our dear students, welcome to the Institute Colloquium at IIT Mandi. Today we have Professor E.D. Jemmis from IISc Bangalore, who will be talking about early questions. Professor E.D. Jemmis is an Year of Science Chair Professor of SERB at Indian Institute of Science, Bangalore. He is working in the area of applied theoretical chemistry. His emphasis is on general questions of structure, bonding and reactivity across the periodic table of elements, searching for relationships between problems in different areas to uncover underlying framework of chemistry. Professor Jemmis studied chemistry at IIT Kanpur, Princeton, and Cornell before joining the faculty of University of Hyderabad in 1980 and IISc Bangalore in 2005. He was the founding director of IISER Thiruvananthapuram between 2008 to 2013. Professor Jemmis' research has been acknowledged through various awards and recognitions, including Shanti Swarup Bhatnagar Prize in 1994, TWAS Prize 2003, and Padma Shri in 2014. With this, I request now Professor E.D. Jemmis to come on the stage and take us through the journey of early questions.
Hello. Yes. Thank you very much for the kind words of introduction.
May I request all of you to please take a seat.
It is an honor. It is an honor for me to be here. It is a rare honor to be in front of such a large group of highly intelligent students. Often one goes to a institution and finds that yes, there are students and teachers, but IIT Mandi is special. There are highly receptive students. I met several of them today, and teachers who are willing to change a sleepy place, Mandi, into a campus that is so vibrant. So I am so glad to be here. I have given a title which is kind of abnormal, early questions. And the reason for that perhaps might become evident as I go along. I will probably say a few words about IIT Mandi again, and I will talk about questions, early questions and not so early questions, questions of various kinds. Then I will talk about an early question I had a long time back, over 50 years ago, and then I come to the implications of that question. That becomes the main part of the talk as much as possible. So this is the plan, and I must say that none of my talks go according to the plan, so do not worry if I get to the end at all. So IIT Mandi, those who haven't been here, they don't know what they are missing. And those who have been here for long do not know what they have. Because, it is such a unique place that you take it for granted, especially those from Himachal Pradesh. and even others who come and stay here for 10 years. But someone who comes for a visit, there is no place like this. There is no campus like this. I thought ISER Thiruvananthapuram campus was the best in terms of natural beauty. I have to change my mind. There is no way that ISER Trivandrum can beat this place. I tell you, in comparison, here when we talk about a mountain, we are talking about sometimes 1,000 meters, 1,500 meters, even 3,000 meters. There they talk about a mountain and it is only maybe 300, that already is too big, right? You see the scale, but then it has to be, this is Himalaya, right? So that's very different. Now, questions, I say early questions. Why? Questions are important because across the world now we realize that this is true. Innovative questions, original innovative questions decides the wealth of a nation, right? So obviously we have to question everything, learn the art of questioning from the beginning. And we don't have to teach you, most of you are really the genius that is available in the country. So you will ask questions anyway. But even if you are not a genius, it is possible to develop the art of asking questions. And that is what is needed. Everyone should be asking questions. Now, questions, when they are early, when I say early, from an individual's point of view, when one is very young, right? But from a civilizational point of view, I would say in the beginning stages of the civilization, in the beginning stages of the human civilization. See, for example, if I were to ask a PhD student who was just finishing, look, think of some good things to do as questions, write a good research project. It is invariably true that a finishing PhD student will give a project related to the general area of his or her research. But if I were to ask this question, somebody who is just beginning the graduate school, has been just admitted for PhD, chances are that the person would give a topic in, say if it is a chemistry department, in some branch of chemistry, right? In physics, in some branch of physics. At least it won't be confined to the narrow topic. But if one can go to a UG student in the first year, suggest some projects, it will be very general, depending on whether the person has been admitted to whatever degree. And I will talk more about this whatever degree soon. But if you can go to the high school and ask them, what do you want to know? What is it that you would like to ask? It will be even more general, right? So it is important to ask questions early on and maybe a list of questions of that kind, so that you have large number of original questions with you. So the habit of asking questions have to begin in the very beginning, if possible, right? And questions become very broad when one is young. When when civilizations were young, right? Questions were necessarily general because everybody did everything. It is not just Aristotle or Plato. It is true of Varahamihira, if you want to go back, did everything possible, whatever questions that were necessary. Aryabhatta was not just one expert in one field. He was an expert in every field that we can think of. So, in many ways, the specializations have been really hindering in some sense. And there I would say IIT Mandi had done a great job. At least in the beginning, they kind of put everybody together, forced them to be together, confined to the same space even, right? So that you look at things in a more broad way. I tell the students now that when you finish and go from IIT Mandi, the whole of your life you will be talking again and again. When I was at IIT Mandi, it was this way. This is what I learned. Now, that is what adding experience to your life. And I will talk about my experience only in different institutions in this context. And what will I talk about? I talk about the necessity of interdisciplinarity. I talk about a mathematician who was studying mathematics as an undergraduate when I was a graduate student. This mathematician went on to be a Rhodes Scholar and did a PhD in mathematics, continued as a mathematician for the next 10 years, and then suddenly felt, look, I need to do something more. I am probably interested in something broader, and decided to learn biology as well. So while continuing as a mathematician, he learned biology. So much so that when Harvard University and MIT together wanted to start the Genomics Institute, called the Broad Institute of Genomics, he was selected as the first director. And you probably know the name, Eric Lander, right? So people who go from mathematics without second thoughts, because as an undergraduate he had learned mathematics, he had learned biology, he had learned many other things, but continued in continued in mathematics until about 15 years later, learning enough to be selected as the director. I talk about another one. Well, before that, let me say something. We have a problem. I said a mathematician who went to biology. We have this problem that after +2, we have to decide what one has to do. It is very unusual to believe that the top 2,000 rank holders in IIT JEE will all want to do computer science. Statistically, it is impossible. And yet, all of them do. Why is it? I don't know. It is the society, it is the parents, it is themselves, it is the friends. I do not know, but that is what happens. I get very upset about this for the following reason. Every year, 1 or 2 people only would resign their high-paying job, a job that pays 5 times the salary of a professor in IISc, resigns the job from an IT company, whether it is Infosys or TCS or Wipro or whatever, and comes back to IISc to say, I would like to do a PhD. And what is more amazing is we ask them, why? Why do you, throw away this job like this? He says, I cannot do this all my life, what I am doing. There are many others who like to do the job and they are doing it. But what is more interesting is that for every one of them who has or not everyone, the 2 or 3 that has the courage in 2 or 3 years to resign that job and come, they say there are many others who stay on in the IT job even if they do not like it, because it is not easy to resign from a job that pays so well after having worked only 5 or 6 or 7 years when you have made commitments of very large kind. This has happened only because of our education system. What is wrong with our education system? Anybody who has enough money, a rich parent, I am talking about people who can afford to pay 60 or 70 lakh a year as tuition fees, send their children to such institutions across the world. Why are they sending them to Yale or Harvard or Princeton or Stanford when they can afford it? What is so great about their education system? They may not even have as bright colleagues in the class as IIT Bombay or IIT Mandi has. Still, why are they sending? It's not just because they have the money. It is because the education system itself is different. How is it different? If you go to one of these institutions, you study several courses, whether it is mathematics, physics, chemistry, engineering, arts, music, performing arts, communication, anything. You take those courses, several of them, and at the end of second year, that means the freshman year is over, I'm talking about now strictly the US language, you finish the second year, the sophomore, and then you have the option to select what you want. And when you select, you have mathematics and music if you wanted, right? Or mathematics and biology, or history and economics with a minor in computer science, or anything else. That option we do not have. We do not have them anywhere. We do not have them anywhere. They say we have started in IIT Bombay. Just minuscule. ICES say we have them. Only math, physics, chemistry, biology. Nothing beyond. Maybe humanities a little bit. Right? So we have a long way to go in our education system. And I say that to the young people because you are the future. At least you people should articulate when you get to the positions of power to change the system. It is not easy. The new education policy actually allows the universities to do, but no university is bold enough to say we scrap the usual program. We will have a 4-year degree admission without worrying in which subject the students are going to be later on. That courage is not there. Everybody is afraid what will happen. Will students come and all will ask for computer science? I think we need a decree coming from the government rather than a gradual change. Maybe that's the only way it will change. Because we have the policy already. We have to enforce it in ways that are interesting. Now, I talked about a mathematician becoming a biologist. I now talk about a historian who became a physicist and a mathematician. Somebody who joined along with me for PhD. I joined for chemistry. He joined for physics. And we asked him, look, how come you were history major? Why did you change? Right? A history major wanting to change and do PhD in physics. Unheard of. It was surprising to us. How come? And we asked him. He said, well, I was studying history. I had good teachers. And I tried hard to go back in time to learn. And I could go only so far. I could go maybe 3,000 years, maybe 4,000. With paleontology, a little bit more. But I want to go even beyond that in history. I wanted to go to the very beginning of the universe itself. And he was smart, of course. He was good enough to get a Fields Medal for developing the mathematics that was needed in his physics. Right? He went into origin of the universe, Big Bang theory in a different way than others have looked at. In field theory, he started what is called string theory. And his name is also familiar. I mean, it's not as though people haven't heard of him. Edward Witten, who started string theory, he had history major and still had the courage to shift. This is the way education should go. It is not very common for us to do this. And I say history. Who is taking history normally? I see people who do not get anything else go to history most of the time here. Actually, again, I look at the institution that I studied, and they have looked at who takes history major in their place after the sophomore year. They found that about 3% of the people who take history come from the top 25% of the admission ranking. The better ones gone on to take history. Why they are taking? Statistics of the same university has been kept for 75 years to find out where are they ending up. And it looks as though most of them, after a PhD perhaps in economics or history or a law degree or maybe a business administration degree, but ultimately after 30 years, many of them happen to be CEOs of large multinational organizations. And then wondered why these organizations are keeping them. Because they have been so serious students of history. They have looked at 50 and 100 years ago, how institutions have evolved, nations have evolved over such long time periods. They have understood the logic of these developments, and they have become true visionaries. And multinationals would like to have visionaries who would think about their institution 10, 20, 30, 40, 50 years from now. And that's what is needed. We really do not have good visionaries. We will not have good visionaries if outstanding minds do not go into history. But then we have this problem of general education. And I again come back to my own university. At this university, at the convocation, the number one student of the graduating batch is given an opportunity of 3 or 4 minutes to speak at the convocation. It is not just the invited speakers, right? And right now a controversy is going on in the United States of valedictorian speech. University of Southern California had invited its valedictorian, the number one student, to give a speech. Her speech was not considered good enough, or not according to what they anticipated. But I'm talking about the valedictorian in 1974, when I had just received my master's degree. That's the only convocation I attended at Princeton. The valedictorian came in, and he had 3 minutes. And he was talking about his first year experience at Princeton. When he came in, there were lots of squirrels in Princeton. The squirrels are all black. There were the squirrels without these 3 lines. And we used to say that, yes, these are squirrels who didn't have the blessing of, remember, the squirrel story, right? He didn't have the blessing of Sri Rama for doing this hard work of constructing the link. But he felt all squirrels in Princeton are black. And they were. But as years went by, and I'm trying to reproduce the words that he used in that short meeting. As years went by, the second year, he felt, yes, the squirrels are back. Third year, he felt, well, they are largely black. But he said, at the podium, he said, look there, that particular squirrel. The only thing I know about that squirrel right now is that at this moment, on this side of it, it is black. Nothing else is certain. He said, my education of 4 years have told me I have to be skeptical about everything. I should not rush to generalizations. This is the education that is provided. I look at everything fresh, right? I say all this because I do not get a chance to talk to such bright minds usually. And you have such a large collection of very, very highly intellectual minds. Now, early UG specialization actually is an antithesis to this idea of broad education. We will not explore things unless one is very, very careful about this, right? So it is time that we collectively, students with their parents and teachers with the university system, the UGC and education ministry and everything else, to stop this compartmentalized education system. How did we get in here? We got it, the BSc physics with mathematics and statistics only. We got it from the British 150 years ago. And the British changed it 100 years ago or 120 years ago. And we are holding on. There is no reason for us to hold on. There will be n number of objections because we are so used to it, from parents, from others. Anyway, let me come to an early question of mine. When I was a first year BSc student at the University College, I had a good teacher, Professor Shankar. He was teaching in organic chemistry, and at that time, this is all that was known about structural inorganic chemistry. There was no graphene, it was graphite. There was no C60, there was no other things that we know about this. But it was so very beautifully explained. Right? Of course, there was already the Huckel rule. This is the tetravalent carbon. That's all that was available. And after he finished this class, he was walking out, and I happened to ask him, is there anything like this for boron? Just casual question. Very, very strange, but very casual question. He was such an elegant teacher. And he told me, look, let us see. We will look at this. So together we looked at this. And Cotton and Wilkinson was the latest book. We are talking about 1968. The book had come out in 64 or 66. There was an Indian edition. And we looked, and there wasn't any answer. I joined IIT Kanpur, and I had good teachers. I asked them the same question. Not really any answer. Is there anything like this boron? The kind of structural chemistry that is there for carbon. I thought maybe I will join the graduate school and maybe I will take this as a topic. And you can't do that because this is what happens. You go with all these questions, and finally you have to agree. I'm going to do what my professor wants me to do, right? So my professor also said, well, you have a good question, but I have no idea how do you go about doing this. So you do this, right? That's what, and so I followed what he said, and I did. But I tell you, gather questions and keep them with you, because these questions will stay with you, and you will not be in this position. You will have many questions. Because if you don't do this on, you will reach so soon here, and I am here now, right? Not far, right? So gather those questions and keep them. This is serious business. The reason I say serious business is the following. See, last 10 years, until 22, including 22, I have been teaching third-year UG students in Indian Institute of Science. We have a 4-year degree. So I have been teaching this course 10 years in a row. And I tell these students, ask your questions, write it down, keep a list of it. And I tell sometimes in the first years as well, you do this. The result is amazing. There's one student who was very systematic in writing these questions. And he continued for the 4th year project with me. He had 3 pages full of questions, most of them in chemistry, some in biology, some in physics. And he was applying to various universities for PhD program. And something unique happened. Among the universities that he applied was Harvard. He said, I have a series of questions that I want to try out. It is hard to believe. Harvard sent him an email saying that we are sending you a 2-way ticket just to come and stay here for 3 days, see Harvard, and come back. Then you can decide whether you want to come. A fully paid ticket. A fully paid ticket. And he went there, he had the visit. He came back and he accepted Harvard. He is in the 5th year there. I'm not making up the story. You can look up, his last name is Kar. Now, this is not unique. There has been 4 more such cases that I know. But the questions that they had were in so different levels, because they were doing this before they got so seriously involved in one topic. So I come back to this. I really see my professor had his problems and I worked on it and I got my degree. But there is something unique there. I did not have to, or nobody in chemistry department at Princeton has to defend the thesis. Instead, one has to give 3 research proposals not connected with the area of your supervisor and submit those research proposals, and those proposals have to be defended. And I had 3 research proposals. I defended them, and they were my starting research projects. I kept it with me. I went on, of course, as a postdoc, but I had that ability that I have 3 research proposals. 2 of them were indeed my first 2 projects. The third one was experimental. I didn't take it. But the question that I had asked, is there anything like this for boron? I worried about it all the time. Didn't get an answer. Didn't get an answer for next 30 years. So I did other things. When I did other things, it went into all kinds of things. I was asking general things, so I had a different way of looking at things. And in this, see, I don't want to give details of one topic, but I could divide what I have done into different kind of headings, or I can give a list of last 4 years, specific projects. None of it is important, but I want to say the old question that I had, that slowly got refined. Is there anything like this for boron? It got refined along with the carbon chemistry that is getting refined. See, the carbon chemistry also became refined. We had graphite, and there was somebody to take 1 sheet out of it. We had C60, and there are a lot of stories about C60 that I can tell because I was kind of seeing what is happening, or the nanotubes. Right? This is a general picture of carbon chemistry that every chemist and many physicists already knows. If it is not in the vocabulary, one would be wondering whether he had a good education. Now, I had to refine the boron question the same way. How is it that we can understand boron? How do we make sense out of it? Are we going to think about borophines, borophytes, or are these the right questions even for the purpose? It was not clear. So I kept on refining it, from 1968 to 1999. And part of the question answers came in 2000. Now, I was planning to start this talk at this point until Saturday. And after coming here, I had talked to people, and then I was told that it is not just the students of chemistry department that will come. So the talk that I had planned begins now, and of course this cannot be completed. So I will really be talking just a little bit of what I wanted to say. There is a chemistry of boron that is analogous to carbon. Then there is a 2-dimensional chemistry that has come out in the last few years, maybe last 5 to 8 years. Then something that is known for a long time, polyhedral boranes at corresponding 3D boron allotropes. And some of you would have seen what is called a Rudolph diagram, those who are in inorganic chemistry, of polyhedral boranes. And that seems to be the equivalent of sp, sp2, sp3 hybridization that defines the total structural chemistry of carbon. That is the equivalent of it in boron, it looks to me. And that is my proposal for your consideration, if I get to it. So analogous to carbon, I will skip this so quickly. It is not as though the chemistry is anything unimportant. A Nobel Prize was given for hydroboration. The chemistry, structurally speaking, is just sp2, sp3, sp hybridization, nothing more. So I skip it very quickly. Now 2D boron, that is more recent. We have benzene to graphene. Everybody understands it. Huckel-Ferrand plus 2 pi electron rule, benzene, naphthalene, anthracene, 2D structure, right? if we take 12 hydrogens out of the icosahedral B12, H12, then also you have this. So there is this flat structure that is available. If I consider that as a 2D structure, I have a network of triangles, right? If I could make something like this, that is like a graphene type of a boron 2D structure, right? It's almost like this, except at the middle of every hexagon, there is one more atom added, right? I mean, I have indicated this specifically with a different color to make that distinction. Now, people have studied this. We were looking at this in 2006, 2007, in that time. And when we were looking at this, before we published, there was a group that published the energetics of this. They said if you consider, if you make a structure like this, it is not even a minima. A striated structure where some atoms go up, some atoms go down is better, so that the energy goes down. This is binding energy per atom. Now, what is more astonishing is that if you remove some atoms from this, make not all hexagons fill, but some of them are kept vacant, then the energy is even better. Instead of minus 6.2, it is minus 6.3. It is even more stable. So this is something unusual. We were wondering why suddenly this. And we had started computing these things, and then in 2007, I had the student Prasad who was working on MgB2 and borophene, but he called it as borograph. And we thought we will continue, and then something unusual happened. What happened is, in 2008, I left it all and took up a job to start ISER Thiruvananthapuram. Next 5 years, I forgot about this, unfortunately. And many things happened in between. And I came back in 2013 and thought maybe I should look at it again. It looks as though some slides go away. It became fully, maybe it was made in some other system. Okay, I will. A new student joined. Prasad graduated and went away in 2008. He's actually a faculty member at IIT Kanpur now. But a student who finished MSc from IIT Kanpur, Nairid Karmoda, joined in 2013. I told him we had stopped something, you should begin again. Can you do this? He was very reluctant. He said, well, it looks like nobody is working in this area. Last 5 years, nobody worked, and you are asking me to start all over again. I said, okay, you start. And he did. What he did was, he looked at every possible calculation that was done by others and said, okay, let us do this whole thing with one particular method so that the energy is comparable. So we have a zero holes structure. Then there is the 1/9 hole density that I was showing the result for. And he put these all as relative energies. The most stable arrangement is not the one without any holes, but with just this 1/9 hole density. That means 1 out of 9 boron atoms, 1 is missing. But if you increase the number of holes, it is high in energy. And so I said, well, how do we understand this? It has been done by others, but how do we understand this? Now, understanding is different things to different people. You see, if it is Coulson, he will say, okay, give us insight. Currently, Frank Nice will say, look, we need insight and numbers. Beginner would say, look, a computer program has reproduced this, but I would like to understand it as well. So it is different things. But we need to have some physical reality when we talk models. When I say physical reality, I mean like this, right? We can have best of measurements and still not do right. We need to be realistic. What we do is not best done by measurement alone. We need to have some way to appreciate this. So we need broad understanding from different point of view for any problem. So, meanwhile, while we are doing this, lots of experiments came. Many experiments, changed the speculation part of it. Suddenly, borofine is made. And when borofine is made, people wondered, is it similar to graphene? And I will say, jumping the gun, it is not just similar to graphene, it is better than graphene. Graphene is hexagonal. This is triangular. Mechanical property itself is better. One can calculate all the other properties, it is better. Why is it not being used? There are other issues that I will come to. We can say, why this 1/9 hole density? Not very difficult to see. I have explained this to +2 students, so it should be easily possible to explain to you also. It is not a very complex thing to do. We have benzene and graphene. We have an equivalent material, MgB2. MgB2 was known for 100 years, but in 2000, Akimitsu measured its conductivity. One finds that it is superconducting at 40 degree Kelvin. This is a few years after a 22 degree Kelvin superconductor brought a Nobel Prize. It was a very complex material. This is a binary material, superconducting at 40 degree Kelvin. It was lying on the shelf. Nobody looked at it. But apart from that, look at this. It is same to graphene because every carbon is replaced by a B minus, and for every 2 B minus there is an Mg+2 from an electron counting point of view. This is alternating layers of Mg and boron. But let us now go the reverse and replace the Mg here by a boron. If you do that, see, they are all boron. They are all boron, so there is no 2 layers. It becomes 1 layer. It is the borofine that we were talking about. Now there is only one problem here. The problem is, this is just the stoichiometry 3 times. The problem is that there is an extra electron. For every Mg that is replaced by boron, there is an extra electron. If you want to go back to the electron structure of graphene, we have to remove these electrons. One way of removing the electron, we need to remove 3 electrons when there are 3 borons extra, right? We just remove 1 boron. Instead of 9, make it 8. Then we are getting back to the same electron count, right? Absolutely no problem. We have the same electron count, and interestingly, you calculate the electronic structure, the band structure, they are similar. Not only they are similar, we can see how we can increase, that is, in graphene, if you want to increase the number of electrons, we replace a carbon by a nitrogen. If you want to decrease, you dope a carbon and replace it by a boron. Here, you only have to increase or decrease the number of holes, and you have a complete control with the same material. Now, this, nothing great, but after computations, an explanation was still waiting. Once we know this, many things can be done. Now, what is the experiment? The experiment is actually on silver 111 surface, boron atoms are deposited, and then using a scanning tunneling electron microscope, you search and see what is the structure. And one finds that there are hexagonal holes, but there are more holes than we said experimentally. Instead of 1/9, that is 1 out of 9, it is often 1 out of 6 or 1 out of 5. And one wondered why. So we calculated again, looking at what happens if it is on a metal surface. Now, if it is on a silver 111 surface, one finds that suddenly what was the best with 1 out of 9 missing is not as good. 1 out of 5 or 1 out of 6 is better. Why is that? And it is not very difficult to find. Why not very difficult to find? It is thermodynamically most stable one that is being formed when we are placing one atom at a time. And if it is to be stable on a metal surface, the metal has to donate electrons. For metal to donate electrons, the layer has to have the requirement. To have the requirement, you make more holes, right? So the silver 111 surface will certainly have a boraphene layer with more holes than what would have been possible on a single layer. This is what is found. And of course, by calculations using partial density of state evaluation, very clearly we can see the donation. I am not going through the detail, right? So the difference is easily explainable. We had put this in 2018, but we asked the question, are there other ways of getting the electron count right other than making holes? And there are. One way is to form a bilayer. Now, what is meant by a bilayer? I think one crucial slide is not seen. I think I had taken slides with two different versions of PowerPoint and put together. So those ones are not seen. Okay, what happens in the bilayer is, let's see if there is another one. Okay, at least I can look at this. See, if we can find that one atom out of this hexagonal pyramid is pushed up, that is, one of the central atoms here is pushed up, another from the top is put down, then we can have a two-center two-electron bond formation. Once you form a two-center two-electron bond between the two layers, we are removing one electron each away from the delocalized picture. And if we can have three such bonds, then we are removing 3 electrons from each layer. So for every 9 boron atoms, if we have 3 such bonds, then we have achieved our goal without any holes. Now, this is published in 2018. It's a speculation. There were 2 other groups also published this result when we didn't know. But I have an explanation, and this is a schematic way of drawing it. Now, one can ask the question, are there any experiments? And, it was really surprising. In year 2022, just 2 years ago, 2 experiments where they have got a bilayer on a silver 111 surface. And you can ask the question immediately, are there only interlayer bonds or are there holes? Interestingly, there are interlayer bonds as we predict, but there are some additional holes here, especially on the part which is on the metal, for the same reasons. Because if there were no holes, there is no requirement of electrons from the metal. So in addition to the interlayer bonds, there are holes. And if you did not have, and if you take an idealized bilayer, it is possible to show that the electronic structure of the bilayer is almost comparable to that of graphene monolayer, even to the extent of showing a Dirac cone, which is so famous for a monolayer graphene. So it is something very unique. We go further. If you have a bilayer that I can represent like this, which means that for every 9 boron atoms, I have 3 bonds. If I make a trilayer, what happens? You see the middle layer has the same bond density, right? For every 9 boron atoms, there are 3 bonds. But if you take the top layer, it has only half the number of bonds, which means that it should have some holes, not some holes. For 18 boron atoms, there should be a hole, right? You calculate that and you find that. So there's a lot one can see. And of course, once you get this, you can think of trilayer, of course, tetralayer, pentalayer. The middle layers will have the right number without any holes. The top and bottom layers will have a different hole. So you see, you are getting into a whole new area of chemistry. It has come to monolayer and bilayer only now. It is expanding. Not surprising. In the beginning, I told you about sp2, sp3, and sp hybridization and talked about diamond and graphite. Then I said there is C60, boraphene, nanotubes and so on. Here we are beginning. In fact, boron chemistry is at a stage what carbon chemistry was maybe 80 years ago from a structural point of view. Well, I will, there are many things going on right now. One would like to get this bilayer and monolayer out of the iron system and do many things with it, but that's not possible easily, but that is what is happening now. The whole world is trying to get it out and put it in a way that can be protected from oxygen and yet use it for materials. I will very quickly run through this. This is common knowledge, polyhedral boranes, the N+1 skeletal electron pair. It's textbook material for last maybe 50 years. There is nothing very different from there. This diagram is a standard textbook diagram. It's there all over. There was a Nobel Prize for polyhedral boranes by Lipscomb. But just as carbon chemistry has reached this far, how do we get the same way to boron chemistry? And that's where one is thinking, where do we begin? Maybe we will begin with the B12H12 This is the most stable arrangement of polyhedral boranes. Why B12H12 there is an explanation. I am not going to go through this detail. Now, I think many things are not coming in because of my mixing up, I see. This is the kind of structure that we have in polyhedral boranes. Now, do not worry about the students. They have their next class or program. So let us keep moving. It is all there in textbooks, what I want to tell from now on already. So it is not necessary that I talk about it. But the 2D part was new. The 3D part that I have to explain are already there. So it doesn't really matter that I don't talk about it. So I will pose this question again, right? We are almost there with answers, and this abstract that I had indicated, there is cyclopropenyl cation, there is B3H5. Using this as a starting material, we can make the 2D structures. If we protonate it, we have a unusual system, B3H6 plus. Using this, we can make all of the polyhedral boranes. From this end, we can make the 3D structures. So we have 3D polyhedral boranes, 3-membered rings, and borophenes. This is possibly a structural model that will come for boron chemistry, just as what we had for the carbon chemistry. Right? I stop at this and thank, of course, IIT Mandi, Garima and Pradeep and all of you for giving me this opportunity. I had good support from various agencies, my students who always had great ways of getting results. And I thank you all for the patience, attention.
Thank you very much, Professor Jemmis, for this interesting talk and letting us know the importance of asking the questions at every stage of our life. The floor is now open for the questions. So, yes.
Good evening, sir. Since you drawed out many comparison between graphene and borophene, so my question is like, now the researchers are exploring various applications of graphene in the field of energy storage and biomedical and biosensors. Does the borophene have the capability to replace in some of the applications? And if so, then we know that India is not so much abundant in terms of the content of boron as compared to graphite, which we have here. Like the most of the reserves of boron is confined to the Central Asia region in Turkey, and we don't have such a good relation with Turkey. So will India be able to is it worthwhile to go into research with borofin if we talk about the industrial dynamics of India?
See, we can argue saying that we don't have as much lithium either, and we are working hard to see how we can still run through the process of electric vehicles. That's one thing. Second is that yes, Turkey is Turkey is one country that has large concentration of boron. So is the United States, and there are 3-4 other countries with smaller percentage. We have very small amounts, but we have some elements that are very important in abundance. So we could trade, and get what we want, right? That is possible. What is important to me is that we are not in a position to do this chemistry for whatever reasons. There are 2 Chinese groups, there are 2 US groups, there is an Australian group. Somehow there is no Indian group working on this even. See, the advantage is if you have graphene, and if you want to have an electron excess graphene, we have to dope with nitrogen, not easy. If you want to have an electron deficient graphene, we have to dope with boron. We do both. But if you have borofin, we do not have to dope with anything else. We have to control the holes only, right? Of course, we have to get the borofin out of the metal surface. And there are several groups trying now how to get it out and then seal it with a silicon dioxide inactive seal. That is the attempt right now so that we can do further. So the first part of your question, I agree. We don't have as much boron, but we have some very valuable elements, and I don't want to tell which these are, which we can trade even with Turkey.
Questions? Yeah, please.
Good evening, sir. It was a very amazing talk. So the question I have is that you told advantage of borofin that we don't need to dope it with other materials. But what other advantages and technological advancements are we looking forward by developing boron chemistry to carbon level?
Yeah, we talk about graphene as mechanically highly rigid. This is far more rigid because hexagonal chain versus triangles. You can easily imagine, right? The mechanical strength to bend a hexagonal sheet versus a triangle sheet. This is very rigid. In fact, once this idea became prevalent, there are at least 50 papers computationally showing the advantages that borofin has over graphene. But those are only computationally shown because the material has to be taken out and experiments have to be done. But the computations very clearly show just about every property, not just one. Not just one. The properties are comparable. The properties that we have of a graphene dimer, where the graphene dimer is always a van der Waals held, the van der Waals bonding held dimer. And then you have the way of looking at the electronic structure and various properties as a function of the interlayer angle. And they are very unusual properties. Now here, we'll have to do the same thing, and people have done that, taking bilayer where the interaction is through two-center two-electron bond, and 2 of the bilayers, how they can be brought, and then the same exercise to be continued. But those are just beginning stages of this, because we haven't taken out the bilayer out of the silver 111 surface. So if you look at literature, large number, last 3 years, 4 years, large number of papers are coming in. It's just exploding because the bilayer came out 2 years ago. The monolayer first time came out in 2015, and then a few groups that has produced it. So this is happening now. So for the question that you are asking, I would say yes, there are many advantages, but maybe you are the one to figure out maximum advantages of this, because it's just the beginning stages.
Okay, thanks a lot, sir.
Front.
Hello. Yes, sir. Thank you, sir, for this talk. So I have a question. Like you wrote in this your slide that the question that you asked was right or not for a purpose. So I want to know that how to find that if these questions are really right, and what to do if they get wrong.
Yes. You know, when I was in the 10th class, we are talking about 1966, when we leave the school, you know, there is no internet, there is no email, nothing of that kind. There are phones in most homes. But when we leave, you know, we have friends, we leave, and we have small books called autograph. So we write something in each other's autograph and, you know, give. And so one thing that people used to ask, people used to write, thinking that these are unquestionables, things that cannot be questioned at all. I remember 3 lines, I will say this. The rose is red, the sky is blue, the honey is sweet, and so are you. Right? Now, they think it is unquestionable. But if you look, the rose is, no, not all roses are red. Not even one rose has red color. There are roses with one flower having multicolors. Now, even if you think a rose is red, what is meant by rose is red? How do you know it is red? You know, the chemistry, physics, biology, engineering of the seeing process that makes you feel it is red. Is that understood? Questions are enormous. We haven't understood really. You know, the mechanism by which an excited state retina molecule gets that process all the way to the brain, which gives you this feeling that it is red. We haven't understood the last bit of it yet. We have lots of questions. There are questions everywhere. But the sky is blue? No, we had that question, but we know the answer already. Right? So that is, you know, so I don't know a direct answer to the question, but I can say that there are plenty of answers and plenty of questions waiting. So my students, undergraduate students, when they bring questions, we sit and say, let us look what is available, what is known. And it is so easy to do now. And they can eliminate them very quickly. Yeah, this is known, this is known, this is known, but this is not. In fact, Pradita Khar, who went to Harvard, had a list of questions. But he got those questions after eliminating whole range of them. So it is possible in this day and age to find out the errors and find out what are valid questions, what are unanswered questions. I don't know if I answered your question.
So let's have more questions then. Okay, I think we got all the questions answered. Oh yeah, we have.
Hello. Thank you, sir, for such an interesting talk. In one of your slides, you have shown one cartoon diagram where there is a process when one starts from the undergraduate studies, and then in the end, he reaches to the research in peace diagram. So, what advice would you like to give to your younger self or to the new faculties like us, how to reverse that process? Because I also understood that current system of academia is something that does not completely support that. So,
yeah, well,
how to realize that in real life? That's it.
I think we have to take advantage of the new education policy, which allows you to be liberal. But people are not courageous enough to take it in hand. No autonomous college has come out with the idea that we will abolish admission to any degree program, but to a general 4-year degree program. Right now, we have that permission, but nobody is coming because the teachers are not wanting to do this, the parents are dead against it, the society is not ready, but we have to do that. We have to do that in the school itself, where every question is encouraged, right? In the university education, I mean, here in IIT, there is an opportunity for the first year students to take all courses, but we are just beginning to do this in a namesake way. We are not bold enough to say IIT Mandi will only admit students for a 4-year degree. We take the best applicants in that, and then allow them to take whatever courses in the next 4 semesters, and then at the end of it let them decide a major. If all of them would like to take, for the sake of argument, computer science, we say, okay, there are only X number of teachers and seats available. There are a lot of repercussions to it. I can see all of you teachers raising 100 different difficulties with it. But if you do not forgo this and say we will do it nevertheless, we will continue to live with what British gave us 150 years ago and what they themselves changed 120 years ago. Shouldn't we start somewhere? I don't know. I mean, it is time that we be brave and institution. I mean, of course, IIT Mandi is a part of 23 IITs now, or 22? 20, yes. So I don't know whether it is obligatory for all IITs to follow the same trend, or one IIT can say, we have decided to do this, come what may. I don't know. I mean, these are questions that you should discuss. This is precisely why I decided to forgo discussing much of boron chemistry and added, as I said, many things in the first 30 minutes almost.
Any more questions? Yeah, Janvi at the back.
Hello, sir. So my question is, how and why did you stick to that boron problem even after 5 years gap?
I was doing many other things which I didn't talk about, and I must say those things are easier to do. I could be a director of a starting institute and still manage to do those things, but this problem I couldn't do, and it was complex enough that I had to put in more time. But I wanted to check when I got back whether it has progressed much. I found out that there were lots of computations, but no understanding. Then I got a student who, Nairit Karmotak, who agreed to do. He will repeat all of these different computations that people have done at different levels, and no comparisons can be made. So he did all these computations again, and we thought, okay, now let us see whether we can understand it. So I came back and looked at it because it was a problem that was difficult, has been bothering me for so long, from 1968, that I was curious what has happened. And it hadn't gone far in the 5 years that I left it, even though many computations were there in between. So I was just curious again to get back.
Further questions? Yeah, please.
Sir, I have a brief question. So this borofin has these triangular faces. So we know that a flat surface, that hexagonal thing can tile a flat surface. So do you think these triangular faces can form curved curvature and lead to maybe CWNT type?
That is what I skipped. So let's see if I can. Yeah. Okay. I will put the question in another way. There are two ways of answering this. First part of it, I will say sp2 hybridization is what is the triangular planar structure that you said graphene. If you say graphene can only be flat, then how do we get tubular graphene structure? We have to strain a little bit, right? How do we get fullerenes? We have to bring in other size rings, right? Now this see here, this is a borospherine, fullerene, borospherine, boron-spherine, B48, B40, experimentally known. This structure is like fullerene, except the view I have taken doesn't show the structures of the atoms in the behind. Now, this has 48 three-membered rings. Yeah, 48 three-membered rings, 2 6-membered rings, that is top and bottom cannot be seen very easily, and 4 7-membered rings. There is one above and another below and 2 on the side. But it is spheroidal if you look at the structure. So it is not sufficient to have 3-membered rings. You should have other rings as well. This is B48. This is even more interesting because this is not only a something like a C70 elongated one, but here between the top and bottom layer there are two center 2 electron bonds, a hexagonal pyramid coming down, another hexagonal pyramid going up. This is also known experimentally, right? These two, and there are many other structures that are of this kind. So true, we have to go beyond 3-membered rings, and these are topics that is happening now. This was known year before last. This was probably 4 years or so ago. So these are developing fields. Just as 1984 was the first time we had C60 categorized. Very first time. It was 1984 only, not earlier. Right? So we have a long way to go in the chemistry of boron. Just beginning. This is known, like a bracelet made experimentally. This one is known. So there are many things that are known. This is a flat B36, like a fragment of this.
Professor Jemmis, the point which you made about an historian becoming a physicist or a mathematician studying something else, and then they are doing higher studies on that. Is it more to do with the personal attribute or the education system there?
Both. I say both. You have a corollary for the question?
Yeah, so why India has such a huge population, why are we not seeing those examples here?
I give you 2 examples. Okay, there is one Professor H.Y. Mohan Ram. Biologists will recognize him. H.Y. Mohan Ram was a famous biologist in Delhi University. Outstanding person. He had a son. Because he was a scientist, he wanted his son to be a scientist. And son was not so much interested, but he was forced to take physics, BSc and so on. He was forced to do a PhD in physics at Cornell University because his father insisted. And so he came back, had his PhD degree and gave it to the father. You can have my PhD degree. Can I now do what I want to do? Now, what did he do? He started the band called Indian Ocean. Indian Ocean at one time was a famous Indian band, started by Anand Mohan Ram, a PhD in theoretical physics. He had one more member in that band who had a PhD in physics. Right? I just give one example. Now, since you live in Bangalore, let me give you one more example. Only one person from India has got 3 Grammy Awards, 3 times. You probably immediately remember the name. You know, he was invited once to IISc campus, and he was talking about his life. He said his father is a medical doctor, and he wanted this gentleman to be also a medical doctor. But he didn't want it, but the father insisted. So he got the degree anyway. He gave it to his father. Can I now do what I want to do? And the father had no choice, right? He wanted to be a musician. His first album got a Grammy for the beginner's album. His name is Ricky Kedge. He got 2 more albums, 2 more Grammys. So it is difficult. Those are individuals with so much of willpower they could do. So we have to also have our society slightly, being taught. And I only hope that the younger students, when they grow up, at least they will let their children to do what they want. Yes, I answered partly at least. Now, our education system, if we do not change, Indians are becoming richer. They will send their children abroad. The ones who can afford this, 4 crore or 2 crore undergraduate education. Our private universities are recognizing this. Private universities have started this process of liberal arts and sciences education. There, if you can afford, but then even that is not within the middle class reach, because these private universities charge somewhere like 8 lakh a year. Not 50, but 8 lakh nevertheless. We will think again. Whether it is Shivanadar University or SRM or, you have these private universities coming up. We would not want that to happen when we have such great institutions of the government. The IITs, the NITs, the ISERs, all of them. So that change is needed. And we have the talent. It's just a willingness and the courage to ignore criticism from people who haven't understood the long-term implications. When someone can do what they like to do, they can do it in the best possible way. Most people do not get that opportunity. And so we live nevertheless.
Are there any more questions? Okay.
Hello, sir. Thank you so much for such an interesting talk. I wanted to ask, boron show this type of chemistry because it forms a very different cluster chemistry formation. Do any such type of borofine structure is present for the boron congeners?
You mean the ones who are heavier than boron?
Yeah.
Well, there are possibilities. We are looking at gallium, for example, right? But even there, see, when we say borofine, unlike graphene and graphite, which is the thermodynamically most stable allotrope, graphite, diamond is less stable from a thermodynamic point of view. But when we talk about borofine, it is not the thermodynamically most stable allotrope. Thermodynamically most stable allotrope is a 3-dimensional one, very complex, and that is the problem that I skipped. I presented it very quickly, saying that it is already known for 20 years. For gallium, it looks as though we could have such structures. But again, not the most stable arrangements. You see, the graphene-like sheets are there, even phosphocene we could think about. We have people thinking about silicene, right? But those are not as stable and having the attractive properties of graphene. The bilayer borofene have that property, right? The heavier ones tend to be more metallic. Once you get to the metallic regime, then all these bonding ideas goes away into a different ways. Like aluminum is not, we can have AL4, CP4 AL4 as a tetrahedron. With difficulty, a few structures of AL12, R12. But when you get to pure aluminum, it is metallic. Right? Then we think about all the things that you have studied about metallic bonding, the arrangement of atoms in in the three-dimensional set, whether it is FCC, BCC, and so on. All those things come in.
Okay, thank you, sir.
So if there are no more questions, then let us thank the speaker. And now I would like to request Professor Aniruddha Chakravarti, our Dean Academics, to kindly felicitate the speaker.
It's not.
Please.
Thank you. Thank you.
May I request all the students to come in front and we can have a group photograph. Thank you very much, sir.